the pulling stress is sigma XA, and the back stress is sigma XB, and the pulling drawing force is FA, and the back force is FB. The back diameter is bigger, which is dB, and front diameter is smaller, and this is the die angle. Alpha is the die angle. So we'll go over these in our question again. So you see, in our industry, it looks like the wire drawing process looks like this one, and these are the rollers, the drawing blocks, and this keeps on. These are the two dies. It is not, it's like successive process of reducing the diameter from maybe a bigger to a smaller and further smaller, so you can put the wire through the drawing process. This is a drawing machine. Multiple drawing processes are shown here, and in this, the cold drawing process is less than half of the melting point. This is an old picture or maybe a sketch showing you the copper wire and self-portrait, the four horsemen. The characteristics, the product sizes, you can go up to 5 microns to several inches with this process, from tiny scale to a very large scale. Mostly they are cold, like less than 40% of the melting point temperature, then it is cold. Small diameter wire uses capstan, and the diameter greater than 1 inch, the rod, full blocks on a draw bench, and so on. You can draw up to fine wire through several dies, speed up to 30 feet per minute. You see, from 30 feet per minute to 300, small diameter goes to 300 feet per minute, to another fine wire goes 5,000 feet per minute, 60 miles per hour or 100 kilometers. This can be very, very fast process for the smaller diameter wire. The die material is made up of high carbon steel, high speed steel, moderate diameter tungsten carbide, smaller diameter diamond inserts. So these are the die material. So this is my die, okay? This is my die, the upper portion and the lower portion, okay? We need to lubricate the drawing process through some coating or oil. And the die angle I mentioned earlier, this is the angle here from this center line to this is our die angle, okay? This alpha is approximately 4 degrees to 6 degrees mentioned here, okay? Typically very small, because the larger the diameter, more wear and tear of the die, and sometimes the die will break. So it is an ideal for smaller diameter. That's why we have successive dies to pull the wire from larger diameter to a smaller diameter. Okay, so now some formulation which you need for your homework problems. So the reduction in area, please write down this formula. You already have drawn this figure. So reduction in area is back diameter or the area back minus area front divided by area back is the reduction in area. And true strain is, you remember, area original or area. You remember the ln. So final area, this may be final. So over here, you remember in the true strain, H final over H initial is also equal to area initial over area final, which is dB. The back area is the initial area. You understood this? And you can also say that 1 is complete 100% area is 1 minus a reduction in area in decimals, maybe 0.2 reduction, then it would be point, suppose 1 over 0.8 would be, this is just an example, but these are the formulation which you need for your homework problems. So how to derive the equation for the stresses, the front stress and the back stress. So let me show you the important equation which you need to know: the power required to pull the wire, how much power required to pull the wire. So if you know sigma x A, so let me show you the drawing process. By the way, this the stress on the right hand side, stress on the left hand side, the material is flowing. This is the slab taken from this portion, okay? And this is a larger view for that. And now I'm going to show you the next derivation process. This is force balance, okay? How do you balance the forces in the x direction? This is a bunch of math. So I'm going to jump to the final formula which you need for your drawing process. Okay, equilibrium. This is still the derivation going on. Then we compare with, we get another equation from Mohr stress circle, that 2 tau flow equals to sigma flow and B equals to, we assume B. Okay, please write down this formula. This is, B is a constant which depends upon the coefficient of friction and the die angle. Agreed? So I'm gonna show you the equation which you need for your homework problems. Yes, use this equation. This is an important equation which you need. Please write down this equation, where B equals to mu over tangent alpha. This is, Stress at the back is the tension. Because it is not just like dangling, it has been taut. Okay, therefore there is a stress at the back. And then stress in the front is a pulling stress, which is also tension. Have you written down this equation? Okay, let's go to the next slide. We also know that the Tresca says that two-top flow will happen when sigma flow is equal to the average stress is equal. So please write down the Tresca for the round part. You can um, use this equation. And suppose if you are using uh, a high temperature, this is a cold, okay? For the temperature greater than half of the melting point, this average yielding stress is equal to C epsilon rate and power M. And this is also average. Now I'm going to show you the next slide. So it depends. You have to check whether it's a hot drawing or cold drawing. Do you also want me to add the formula in the test, or will you will bring your own formula sheet? You will also bring, I will provide you. Okay, suppose if you forget some formulation, then you can still see in our test. So have you understood this? The sigma flow for hot is strength coefficient C epsilon rate, and epsilon rate has this formula for, it's a lengthy formula. VB is the velocity of B side, A is the area. Do you have access to these slides? Yes. You know, stress circle, there's a sigma x, plus P. This is the average point here. Sigma x plus P over 2. This is equal to y, or two-top flow. I would say this is the radius. What is this? Average point is radius. Radius is also equal to shear stress in flow. So that's why if you bring 2 over here, we bring sigma x plus P equals to top flow, or you take sigma over there. Okay, this is about the more stress circle. Now you see, if we have back tension, we are reducing the pulling power. The die pressure is reduced. When you have a back tension, then the stresses, their pressure are reduced. So it's good to have a back pull during the process. It reduces the motor power to draw the wire inside. Okay, let's solve this problem. So let's solve the previous equation with alpha equals to 6 degree. This is our alpha, okay? This is my die, the upper portion, the die, the lower portion, and this is our center line, and this is my angle alpha, and this is my uh, material going to be reduced here. It's just a rough sketch. Sigma XA, sigma X tension B at the back side, XA power law equal to K epsilon the power N, and K is given 760 megapascal, N is given 0.19, and right now it says back stress is 0. So mu is given. Okay. The draw stress for failure, draw stress should be equal to material flow yield stress. And you know the formula for that? This equation, I just showed you this equation. If you plug in the values here, sigma XA is K epsilon. This is K epsilon to the power N, and this is the average N over N plus 1. And this is 0. Everything is because back stress is 0, and you are left with this term. B in our case, 1. Okay? Mu over tangent alpha. Can you calculate? Let me see. Mu equals to 0.1 over tangent alpha. About 1, assuming is 0.95, assuming is 1. Okay, so B is equal to 1 plus 1 over 2, so the reduction in area equals to 0.6. What is this? This is reduction in area. Okay, RA 1 minus diameter front over diameter back square. So I can write here 1.19 over 1 equals to 2 times RA. Agreed? Because this is my whole RA, and from here, if you do the math, is 1.19 divided by 2. About 60% reduction in area, which is given here. You understood this problem? Energy per unit volume is represented by letter U. You will also see the same letter U in our machining process. U is energy per unit volume. Sigma XA with no back stress here. Okay, let's do another problem. Determine the power and plot sigma X and P along the die. the formula we have the front stress for two-top flow the back stress in our case the good thing is the back stress is 0, so the whole term goes to 0. Okay, the front diameter is 13 millimeter. I will say dB. This is B letter. Okay, letter B. And the front diameter, this is the back diameter, the front diameter is 12. So we are reducing the wire from 13 millimeter to 12 millimeter, and the speed of the wire is 1.5 meters per second. The K value is given, N value is given, alpha is given, mu is given. So can you calculate? Let's do the math here. B equals to mu over tangent alpha. Our mu is coefficient of friction between the die and the workpiece. Alpha equals to 4 degree. Please open your calculator and help your professor. And if you do the math, do you get 1.43? That's good. This B is gonna go over here, okay? It's gonna go over here. So 3 places. Okay. Now you have to find out the power. Make sure you understand the power formula. Force times the velocity. Velocity is given. Okay. This is the velocity. You have to find out the drawing force. And the pressure, I would say pressure, force per unit area. We will come back to this one. Okay. So two top flow. Let's calculate this two top flow. Can you help me calculating the two top flow terminology? What is two top flow? It is the average cooling side. Is it cold drawing? Yes. It is not mentioned, so you will assume it is cold drawing. So for that, the average stress equals to this value. I think I mentioned it earlier. Let me show you the average. Yes, for the cold drawing. You see that? Can you calculate that two-top flow, which is the denominator of the left-hand side? Two-top flow equals to K, which is 760 megapascal. Epsilon. So the true strain, how will you calculate the true strain? You will use this formula 1 over ln 1 over 1 minus reduction in area, and 1 means 100%, 1 minus Ra. What is Ra? Ra equals to 1 minus dA over dB whole square. This will be in decimals. So 1 minus dA is 12, dB is 13 square, and if you do the math, do you get 0.15? That is equal to 15% reduction in the area of the wire. And that value 0.15, you plug it in over here, ln 1 over 1 minus 0.15. How much do you get? 0.16. That value you plug it in over here, 0.16. What is N? N equals to 0.19. Okay, 0.19. Now we are left 1.19. What is 2 tau flow? Can you help your professor? Is it 446 megapascal? Just confirming with you. Yes, you got it? Okay, I give you some time to verify this answer. I want to show you one more thing here. You got it? Yeah, 1.19. Let me tell you one thing very important. If this process is valid or not, let me show you. Because you have to use this equation, assuming the back stress is 0. And then for the minimum diameter, what is dA? Although over here, the minimum diameter is 12 millimeter, but you can calculate this one with the condition that the front stress and the yielding this if this is equal to 1, for when you say that the sigma xa equals to 2 tau flow, which means this is left hand side, so 1 plus 1 point, sorry, what is our b? It was 1.143, right? 1.43 divided by 1.43, 1 minus dA minimum. What is the minimum area? Now, why did I say that it's 1? If it is greater than 1, it is good thing that you are pulling with a greater force, required force to flow to let the material flow. You see my point? But suppose if you are just at the threshold, which is required by Mohr stress circle, 2 tau flow should be the minimum stress to deform the material. You see my point? That's why we are assuming what should be the minimum diameter. The Can you calculate? So from this math, dA minimum comes out to be 8.53 millimeter. So we are good that our diameter is 12 millimeters. So this die angle will work. Okay, because our diameter minimum we can achieve from this die is 8.53, but we are pulling with a greater stress and some other values, so this diameter is achievable. That's what. But if you go below 8.53, this diameter, it will not be achievable. You have to change the die angle. You see my point? So let me show. Yes. Yeah, 13 millimeter. Now let's do the question number sigma xa. Let's plug it in over here. with the actual value. So I'm gonna show you what is my sigma XA. I want to calculate sigma XA with the original diameter, which was 12. You see my point? What is my original diameter? 12 here, and the back diameter is 13. And now you can calculate the actual ratio. What is sigma XA? Can you tell me what was 2 tau flow, which is 446 megapascal? Agreed. So let me write down here. Sigma XA over 446 megapascal equals to 1 plus 1.43. You have 1.43. 1 minus 12 over 13. Now you open your calculators and help me. What do you get? You get 0.35. If yes, the front stress equals to 0.35 times 446 megapascal. So with that, we just have 156 megapascal because we are not reducing it to 8.53 millimeter. Therefore, we don't need that much sigma XA. You see my point? So this is your pulling drawing stress. So can you find out the area? If you know the stress, force per unit area, that means the drawing force. I would say F drawing force would be equal to sigma XA times the area. And you know that the wire diameter is reduced to 12 millimeter. Okay. What is the area of the wire which has been drawn? Pi d square. I would say dA square over 4. Can you help me finding out the drawing force? 12 millimeter. 156 10 to the power 6. I would say let's convert it into pascals. You found it? What is the drawing force? Is it 17.6 kilonewtons? Let me double check in my computer whether I get the same answer or no. 5 by 4 times 0.012 square and 156. Yes, I get the same answer. 17.64 kilonewtons. Do you know in pound force how to go from newtons to pounds? You know the conversion? One pound, 1 pound force equal to 4.45 newtons. And you can go from here 4.45 newtons equals to 1 pound force. Let me change kilo to thousand. Now you can just do the math here. Okay, let's do the math here. So 17 0.643 divided by 4.45. About 3,964 pound force required to reduce the diameter to 12 millimeter. And you know the power equals to drawing force times the speed. The speed is given, which is about 1.5 meters per second. So you need to use the kilonewtons or newtons here, 17,643 newtons times 1.5. 26.4 kilowatts. The or how to go from kilowatts to horsepower of the motor. Let me show you. 1 horsepower, 746 or 0.4746 kilowatts. So you can easily convert this into horsepower. 0.746 kilowatts equals to 1 horsepower. That will give you the answer 35.4 horsepower. This should be the power required to pull the wire power of the motor. Do you understand this question? Will you be able to solve such problem in your exam? Any question, ladies and gentlemen? So therefore, I probably mention one thing here: sigma xa or 2 tau flow. If to find out the minimum diameter. So you know how to find the minimum diameter. So just go over this problem again. Assalamu alaikum. Sorry, this class. I will take this. Maybe you can understand this question at home. I would suggest you do this problem again at home. Yeah.
Watts. Just for that. Horsepower was used more. How fast it could spool it. The torque was more inches per wattage.
Force time velocity is the power, yes. But you know that much force times velocity is the motor pulling that with the velocity. So the whole process is done by the motor. Motor is turning that speed. I think there are some 35 horsepower motors in the market for the big drawing manufacturing process. When you go to industry, they might have bigger motors, custom made motors. But the one which we use usually 1/3 or 1/4 size. Will you practice this again? Okay. I give you a minimum 5 minutes, 10 minutes break, and we come back.